Hello all. This is going to be a paper 3, okay? So this one is for the people who are watching from the UK mostly, I think, and also from the United Arab Emirates maybe, but this is a thing I never asked for, but please let me know where you're watching from in the comments. It will be nice. So this paper 3 is a recent one. It's from June 2024, and it's Edexcel level 3 GCE. And sadly, I realized that I only have one past paper 3, and that's from 2025. So it's the most recent one. So anyway, hopefully in the future I will keep making these videos. So I will populate the channel with more paper 3 videos and paper 2, paper 1, core physics 1 and stuff like that from England. I think this test is taken this Friday, I think, maybe, or maybe Monday. Let me know in the comments again. And let's dive in because I'm recording this on a Wednesday. Yeah, it's Wednesday. On a Wednesday afternoon, after my sister left the office, so it's quiet and I can record these videos. Sadly, I don't have a quiet place to go and record these videos. So yeah, my life situation is not great, really. But what keeps me going is that you guys write really nice things. Sometimes you find these videos useful. So anyway, let's start because I want to finish this as fast as possible without doing any discounts on quality, of course. So question 1, and by the way, I think paper 3 is the equivalent of somewhat of, it's some sort of a combination between unit 3 and unit 6 from the international curriculum. And unit 3 and unit 6 are experimental kind of papers. So this one is kind of experimental. I mean, they give you measurements, you have to do experiments, etc. So experiments, I mean virtual experiments, because they are not going to ask you to perform an experiment in the test. So the other thing is that this is a test that is 2 hours and 30 minutes long. So try to spend about a minute per mark in your question. So if a question awards 10 marks, it should take you 10 minutes and so on and so forth. So question 1. A student stretched a length of nylon fishing line using the apparatus shown below. Okay. You have the clamp there and you have the nylon string on which you attach some weight. So the nylon, give me a second to take care of this. Okay, good. So the nylon fishing line was stretched by adding masses to the mass holder. The positions of the bottom of the mass holder were measured as masses were added. For each mass, the extension of the nylon fishing line was calculated. The student recorded the results as shown in the table. Criticize the recording of these results. So the first thing we can write is that the position of the mass holder, okay, has not been recorded. Okay, and only delta x, the extension, was recorded. Okay, it will be nice if we could somehow tell where the final position was and so on. So there is no such measurement. We don't have enough space, so we're going to use a clean space to continue with questioning. Another thing is that data not recorded to a consistent number of significant figures. Okay, and sometimes, and we specifically refer to the mass. So mass was reported at 1 or 2 significant figures. So it should be consistent throughout. So you can see here we have 0.1, 0.25, 0.5, etc. So this is one significant figure, this is two significant figures, okay? So that's kind of problematic. So these are the only things we can write, really. I mean, the data are not that bad to be criticized. So I don't know if they were searching for something else, but this is a proper answer, I believe. So let's move on to part B. Okay, part B, describe how the extension of the nylon fishing line could have been determined as accurately as possible. So the first one is to read the meter rule at eye level to avoid parallax error. Okay, so that's the first thing we can do. We can use a set square. So use a set square against the bottom of the mass holder, excuse me, to get a precise position reading. Okay, so that's the other thing we can do. So we can also record positions when loading and unloading. Oops, yeah, okay. Loading and unloading. And then calculate the mean extension. Okay, part C. The strain for the nylon fishing line at its yield point is 0.04. State what is meant by yield point. So it's the value of stress, the yield point, okay? It's the value of stress at which the fishing line, okay, begins to deform plastically. Okay, I'm gonna use a clean page. So plastically, okay, or we can also say at which, or the stress at which it continues to extend with no further increase in mass. Okay, so once it reaches the yield point, for the same stress, it will continue to extend until it breaks eventually, right? So, okay, that's the answer. Part 2. The original length of the nylon fishing line was 2 meters. Determine whether the fishing line was stretched beyond its yield point. So, the strain is delta x over L, okay? So delta x max is going to be 0.04, okay, which is the strain for the nylon fishing line at its yield point, okay, times the length, which is 2 meters, which yields 0.08 meters, which is also equal to 8 centimeters. So, but max extension from the table, okay, is, let's go see. So in the table, the maximum extension is 7.2 centimeters, okay, is 7.2 centimeters, which is less than 8 centimeters. So we don't go beyond the yield point. Okay, that's the answer. So this was problem 1, okay. I hope this was a good start. One of the problems about recording paper 3, the same goes for unit 3 and unit 6 from the international curriculum. And the same goes for mechanics. I tried to record mechanics papers. They involve too much writing, so I have to write a lot of sentences. And for the mechanics case, it's a lot of calculations, so it's difficult to actually walk through these calculations on a video. Okay, so yeah, I don't know if that makes sense, but it's difficult. So anyway, let's move on to part two. To question two. Okay, question two. A student made measurements to determine if some gold coins were made from pure gold. The coins that were available to the student are shown below. The student used digital calipers to measure the thickness T and the diameter D of one of those coins. Question I, calculate the volume V of the coin and the percentage uncertainty in V. Okay, so let me draw it here actually. So, I don't know, the side. Okay, I mean, from the side, the coin looks like this. So it's kind of, it's cylindrical. Okay, so this is what I'm trying to say. So the volume of a cylinder is pi r squared times the height, where the height in this case is the thickness T. Okay, so it's actually pi r squared times T. And since they give us the diameter, we have to use d squared over 4 times T, because of course R is D over 2. Okay, so let's write this down. So V is pi d squared T over 4. Okay, to pi 22.16 squared times 1.54 over 4, and that's millimeters cubed. So that's equal to 593.95 cubic millimeters. And to convert, let me think. Okay, and to convert to meters, we have 593 times 0.95, and then to convert to meters, 1 millimeter is 10 to the negative 3, and then we have to take the cube of that, so meters cubed. I hope this makes sense and I didn't lose you. So eventually we find 5.94 times 10 to the negative 7 cubic meters for the volume. Okay, now we need to find the percentage uncertainty. First of all, we need the absolute uncertainty. So the absolute uncertainty in T, the thickness, is actually the same as the absolute uncertainty in D. And let me read. So the student used digital calipers. Okay, so for digital calipers, we know that the resolution, so resolution is 0.01 millimeters. Okay, so for the absolute uncertainty, we take half the resolution. So resolution over 2. Okay, so the absolute uncertainty is always half the smallest deviation, the smallest resolution of the instrument we use. So in this case, 0.01 over 2 or 0.005 millimeters, right? Okay, now, since this is a product of quantities, the percentage uncertainty is the sum. So the percentage uncertainty in V is equal, and the constants don't count when we deal with percentage uncertainty. So we have the percentage uncertainty in D squared plus the percentage uncertainty in T, and then we need an extra step. The percentage uncertainty of a power is the power times the percentage uncertainty of the quantity. So what I mean is that percentage uncertainty in D squared is equal to 2 times the percentage uncertainty in D plus the percentage uncertainty in T. And I have a video about this. It's titled Unit 6 Uncertainties. It's the same as the uncertainties you will need here, guys, okay? So search it up. Okay, we're not done yet though. Let me use a clean page. And okay, we're gonna move to that clean page. Okay, So we have 2 times the percentage uncertainty in D, which is 0.005 over 22.16 times 100 plus 0.05 over 1.54 times 100, and this is equal to 0.045 plus 0.325, which is 0.37%. Okay, I hope this makes sense. This is what they ask, right? Calculate the volume of V and the percentage uncertainty. Okay, so we found the volume and the percentage uncertainty. So we are ready to move on. Part 2. The student measured the mass of the coin using an electronic balance. The balance had a resolution of 0.1 grams. Again, when they tell us that the resolution is 0.1 grams, this means that the absolute uncertainty in the recording of the mass is half of that, so 0.05 grams. Okay, so assess whether the coin could be made from pure gold, and they give us the density of pure gold and the mass of the coin. So, first of all, let's start with what I just said. So the absolute uncertainty in the mass is 0.1 over 2 grams, so 0.05 grams. Okay, now the density is mass per volume, or 11.2 grams, which we will convert to kilograms because we need to compare with what they give us, with the density of gold that they give us, and it's given in kilograms per cubic meter, so we convert grams to kilograms. The volume was just calculated as 5.94 times 10 to the negative 7 cubic meters. So we find 1.89 times 10 to the 4 kilograms per cubic meters, but we are not done yet. Okay, so it's a long problem. Now let's find the percentage uncertainty in rho. By the way, whenever we have physical quantities that are multiplied or divided, we always calculate the percentage uncertainty. So this is why we calculated the percentage uncertainty of the volume, and we will do the same with density. So the percentage uncertainty in rho, and the reason why we need the uncertainty is to be able to compare what we found, the 1.89 times 10 to the 4 kilograms per cubic meters, with the density of pure gold that they give us. Okay, so the percentage uncertainty in rho is equal to the percentage uncertainty in the mass plus the percentage uncertainty in the volume. So the percentage uncertainty in the mass is 0.05 over 11.2 times 100 plus 0.37%, which was calculated earlier, or 0.82%. We are still not done. Okay, once we have the percentage uncertainty, we can find the absolute uncertainty. Okay, so the absolute uncertainty in rho is equal to the percentage uncertainty in rho times rho, what we just calculated. Or, let me think, 0.82%, or okay, let me write it like that, 0.82 times over 100 times 1.89 times 10 to the 4 kilograms per cubic meters. This is equal to 154.98 kilograms per cubic meters, or 0.015 times 10 to the 4 kilograms per cubic meters. Okay, so the maximum density we can have is equal to rho plus the absolute uncertainty, plus the absolute uncertainty in rho. So 1.89 times 10 to the 4 plus 0.015 times 10 to the 4, which yields 1.91 times 10 to the 4 kilograms per cubic meters, which is less than 1.93 times 10 to the 4 kilograms per cubic meters, which is the density of pure gold. So actually not, this is not pure gold. Okay. Okay, part B. The student's experimental method could have been improved. Explain 2 changes the student could have made to the experimental method. Okay, so first of all, you can, he or she, I don't remember, they can measure the thickness of a stack of coins. Okay, and of course, and divide by the number of coins. Okay, so the absolute uncertainty of the thickness stays the same, but the percentage uncertainty in the thickness reduces if they have done that. Okay, significantly actually, because you divide it is basically divided by the increased by the number of coins pretty much. Okay, so it's you're going to have a really tiny percentage uncertainty. And the other change is that they could repeat each measurement of diameter, thickness, and mass several times. Okay, and calculate the mean. Okay, this reduces the effect of random errors. So random errors in this case will be an irregular coin, for example, okay, that gives you an irregular thickness. Or, I don't know, some random error in the mass measurement due to the balance or due to, I don't know, some dust on the coin or something like that, okay? So if you take multiple measurements, you average that out. Okay, so now we are done with question 2. Forgive me, I thought we were done after calculating all those percentage uncertainties, etc. So it turns out we were not done. So let's move on now to question number 3. Okay, question 3 is a long writing problem. Okay, you see the asterisk there, which are my absolute favorites, not. Okay. Okay, I shouldn't say these things publicly to students, but anyway, I actually prefer to perform calculations. I mean, I'm a physicist. So anyway, what do I want to say about this? Oh, so it awards 6 marks. So apart from, except for spending about 6 minutes, give or take, on these problems, when it's a writing problem, you should provide about 6 sentences, between 5 to 7 sentences, to answer questions such as these. Okay, so I mean, these are some general exam techniques. So we have this circuit, excuse me. A student connects 3 identical 3-volt bulbs to a 6-volt battery of negligible internal resistance. The circuit includes 2 switches, S1 and S2 as shown. The student closes S1 and records the brightness of each bulb. Okay, before we answer, let's see what's going on. So if you close this switch, you will have current, the same current flowing through bulb 1 and 2. Okay, so in this case, we have the 2 bulbs in series, so the same current flows through them. They will have the same brightness, right? Now, okay, let's continue. So this is the general remark when we close switch S1. And then with S1 still closed, the student closes S2. Explain how the brightness of bulb 1 compares with the brightness of bulb 2 before and after S2 is closed. Okay, so with S1 closed, bulb 1 and bulb 2 will share the same brightness, okay, because they are in series. But if you close switch S2, Now you see that we have these bulb 1 and bulb 3 are connected in parallel. Okay, so their resistance reduces pretty much. Okay, and a different current will flow through bulb 1 and 3 and bulb 2. Okay, so things will change. So let's go see what's going to change. So first thing first, before S2 is closed, okay, and with okay, and of course, and with S1 closed, okay, and with S1 switch closed, okay, bulbs 1 and 2 are in series, okay, so they carry the same current, okay, and have the same potential difference across them. Hence, they glow with equal brightness. Oops. Okay. Now closing S2 connects bulb. Oops. Yes. Okay. Bulb 3 in parallel with bulb 1. Okay. So bulbs let me think. Okay. And then we can write in parentheses the combination. So the combined bulb 1 and 3 are in series with bulb 2. Okay, so this is a different situation now. So the combined resistance, okay, of bulbs 1 and 3 in parallel is less than the resistance of bulb 1 alone. Okay, now we'll need an extra page. I'm sorry for writing so many things, and I'm sorry for writing dense answers, but I want you to understand what's going on. Okay, so let's move on to the next point. This means the total resistance of the circuit decreases, so the current through bulb 2 increases and bulb 2 gets brighter. Okay, now the potential difference across the parallel combination, okay, so 1 and 3, I mean bulbs 1 and 3, decreases, okay, because more voltage is dropped across bulb 2. Okay, the current through bulb 1 decreases, so bulb 1 gets dimmer. Okay, so after S2 is closed, bulb 1 is less bright than bulb 2. Okay, so this is a complete answer for this problem, I believe. All right, we're ready to move on to problem number 4. This was another long problem, guys. So this is a difficult test, I think. I mean, paper 3, because it's long. I mean, too many questions, too many things to write, too many things to think about. So I wish you the best of luck, guys, but I wouldn't want to take this test right now. even though I have a PhD, but still, I mean, I'm older, guys. I can't keep up with you. So anyway, let's move on to the next question. Okay, let us move to question number 4 now. Helium is available in small metal canisters. The helium can be used to fill party balloons. The legend is that you can also use it you can also inhale it and sound funny. I never tried that, but if you did, let me know in the comments. So, a full canister contains helium gas at a temperature of 18.5 degrees Celsius and a pressure of 1.65 times 10 to the 7 pascals. The canister is approximately spherical with a radius of 4.36 times 10 to the negative 2 meters. Calculate the mass of helium gas in the full canister, and they give you the mass of 6.02 times 10 to the 23 atoms of helium as 4 times 10 to the negative 3 kilograms. What is this number called, by the way? Let me know in the comments. Shall I tell you the answer? I'm not going to tell you the answer. But this number is very special in physics. Actually, in chemistry too. Actually, it's more important in chemistry than in physics. But let me know what the name of that number is. Okay. So let's do this. We're gonna use the ideal gas law. PV is nKT. We need to find the number of molecules. So P times V over KT. So let's plug in the numbers. 1.65 times 10 to the 7 pascals, and a pascal is given in newtons. Sorry, 1 pascal is 1 newton per square meter. And then this is a spherical thing, so the volume is 4/3 pi times the radius cubed, and the radius is 4.36 times 10 to the negative 2 cubed meters cubed. Okay, beautiful. And then K is 1.38 times 10 to the negative 23, and it's in units of joules per Kelvin, right? Times the temperature. Don't forget to convert to kelvins by adding 273. So 273 plus 18.5 kelvins. Okay, kelvins cancel. Then we can cancel the square meters. Then notice that newtons times meters is joules, and therefore all the units are cancelled, and this is a pure number, which is what you should have, right? Because this is the number of particles. Okay, so it should be a pure number, and it's equal to 1.42 times 10 to the 24. Now n over 6.02 times 10 to the 23rd is 1.42 times 10 to the 24, oops, over 6.02 times 10 to the 23, and this is equal to 2.37. So the mass is 2.37. Don't know what happened to my handwriting. It always deteriorates. 2.37 times 4 times 10 to the negative 3 kilograms. This is 9.5 times 10 to the negative 3 kilograms. So basically 9.5 grams. So tiny amount. So moving on. B. Student X and student Y discuss the weight of the canister and its contents after a number of balloons have been filled. Student X suggests that the weight will have increased because the upthrust exerted on the canister by the helium will be reduced. Student Y suggests that the weight will have decreased because helium has been released from the canister. Assess which student's suggestion is correct. Actually, what student X suggests is something that it never crossed my mind. I would have never thought about that, to be honest. So, and it turns out that it's wrong. So, okay, that's good that I don't have wrong thoughts, I guess. When it comes to physics, at least. No, I do. Very frequently, I make mistakes. So, upthrust on an object, okay, equals the weight of fluid displaced. Okay, the canister is a rigid, is a rigid metal container. Okay, so its volume does not change as helium is released. Okay, so because V is constant, okay, the upthrust from the surrounding air and not the helium gas, okay, the surrounding air, okay, the surrounding air stays constant. Okay, so student X is wrong. Okay, I hope it makes sense. So you have a canister with some helium inside it. So releasing this gas does not do anything to the volume. I mean, the volume is the same, right? You do not immerse it into something, so you have upthrust. Okay, so this statement makes no sense by student X. Okay, let's examine the statement of student Y though. So as helium is released, okay, the mass of gas inside the canister decreases. Okay, therefore, the total weight of the canister plus its content decreases. So student Y is actually correct. Student Y is correct. But the caveat is that we're talking about the metal canister with 9.5 grams of helium gas. So if you remove 4 grams out of a steel canister that weighs, I don't know, 10 kilograms, it's still not a measurable thing, really. So, yeah, I mean, this question, I mean, the part B is kind of strange, to be honest. For me, it feels strange, but it's a nice question to ask. It's good to think about things in physics, especially things that don't immediately make sense. So perhaps not for the A levels, but maybe for those of you who are going to study physics at a higher level later in your lives, or engineering. All right, let's move on to question number 5. Okay, question number 5. A student used springs to attach a trolley between two fixed supports as shown. So, I mean, if we move the trolley to the right, for example, this spring is going to be compressed and the other one is going to be extended. So we're going to have a push that way and then vice versa, okay? So oscillations will occur. When displaced horizontally, the trolley oscillated with simple harmonic motion. To determine the time period t of oscillation of the trolley, the student displaced the trolley from its equilibrium position and released it. As she released the trolley, she started the stopwatch. She stopped the stopwatch when the trolley had returned to its original point, to its starting point. Question A, explain how the procedure used by the student to determine T could have been improved. So the student can take a large number of complete oscillations. So we can write this down first. Time a large number of oscillations, okay, and divide to find the mean, okay, the mean period, okay. This reduces the percentage uncertainty in T. Okay, the other thing we can do is to allow the trolley to oscillate for a few cycles before starting to time. starting timing, okay, to allow the oscillation to settle, because there might be some irregular motion in the beginning, okay. Use a marker at the equilibrium position, okay, so it is clear exactly when the trolley passes a fixed reference point, okay. And the final thing I'm going to write here is time from the equilibrium position, okay, where the trolley is moving faster, okay. This minimizes reaction time, okay. So these are some of the things the student can do. Let's move on. Part B, the mass of the trolley was capital M. The student added a small mass, lowercase m, to the trolley and determined the new value of t. She repeated the procedure for a range of values of m. She plotted a graph of t squared against lowercase m. Explain how she could use her graph to determine a value for m. Okay, so the period for this oscillation is going to be 2 pi times the square root of m plus m over k, where k is the k of the spring and capital M is the mass of the trolley, okay. So if we square this, we have 4 pi squared over k times m plus capital M, which we can rearrange as t squared is equal to 4 pi squared over k times m plus 4 pi squared over k times capital M, okay. So this is of the form y equals mx plus c with the gradient equal to, okay, y is going to be t squared, x is going to be m, and m is the gradient there, okay. So don't confuse this m. Maybe I can write this as I don't know, k, no, m1 maybe, okay. So that's the gradient. I mean, m1 is the gradient and c is the y-intercept. So the gradient in this case is going to be equal to 4 pi squared over k, okay, and y-intercept is equal to 4 pi squared over k times m, okay. So you can use the y-intercept to calculate m, and also notice that y-intercept over gradient is actually equal to m, okay. So if you calculate the y-intercept and divide by the gradient, that's automatically m, the value of m that you're looking for, okay. Okay, this was question 5. It awarded 10 marks, okay. So, but it's also a long problem. So let's move on to question number 6. Okay, question 6. Roslyn Chapel. I've never heard of it before. If you visited or know about it, let me know in the comments. So Roslyn Chapel is a 15th century chapel in Scotland. Inside the chapel, small sandstone cubes protrude from a number of arches. It has been suggested that carvings of these cubes bear a resemblance to standing wave patterns that can be produced on a vibrating metal plate. A metal plate is made to vibrate and sand is scattered evenly across its surface. At a certain frequency, the sand moves to produce the standing wave pattern shown below. Okay, we have a vibrating metal plate and that pattern. Question A, explain why the sand moves to different positions when a standing wave is formed on the plate. So we can write that the standing wave forms on the plate. So this is a 2D standing wave, so it's kind of a strange question for you guys, but not for someone who will later go on at the university, okay, because you study things like this. So a standing wave forms on the plate, okay, which has nodes and antinodes. Okay, so at the antinodes, the plate vibrates with maximum amplitude. Okay, so sound is thrown away from these regions. Okay, so sound collects and stays at the nodes, okay, where there is no vibration. Okay, so this is the answer. Okay, let's move on to part B. The plate is set into movement by vibration generator. The wavelength of the waves produced in the plate was estimated to be 0.32 meters. The signal applied to the vibration generator is shown on the oscilloscope trace below. The time base of the oscilloscope was set to 0.5 milliseconds per division. The waves produced in the plate travel at a speed much less than the speed of sound in air. Evaluate whether the data supports a value for the speed of waves in the plate that is much less than the speed of sound in air. Okay, so the period for these waves, I mean, if we start from somewhere there and trace one full cycle, we have about 4.5 deviations. So 1, 2, 3, 4, and then about a half. So the period is 4.5 deviation times 0.5 milliseconds per deviation. Okay, so deviation cancels. So it's kind of a weird unit, but you can do that. Okay, so 2.25 milliseconds is the period. The velocity of a wave is the wavelength times the frequency. So the frequency is 1 over the period. So we can write that as lambda over the period. So lambda is given as 0.32 meters over 2.25 times 10 to the negative 3 seconds. So that's 142.2 meters per second, which is less than 300 meters per second, which is the speed of sound. So the statement is true. Okay, let's move on to part C. The speed of sound in air can be determined by creating a standing wave in a column of air. Okay, the diagram shows a tuning fork just above the open end of a tube, and actually it's kind of a strange arrangement, but this is the tube that they mean. Okay, so it's called the perspex tube. Actually, let me draw straight lines. Okay, so that's the tube. Okay, so this is the tube. Okay, and this tube is immersed in water, which is contained in a cylinder. Okay, the tuning fork produces a sound wave of known frequency f. Several tuning forks are available, each with a different frequency. A student adjusted the length L of the air column, so that's the L, we see it there. Okay, a loud sound was heard when a standing wave was produced. A node was formed at the surface of water, and an antinode was formed at the open end of the tube. The student used values of L and F to determine a value for the speed of sound. Describe a graphical method that the student could have used to determine a value for the speed of sound. So first of all, let's draw the wave. So the wave will look like this. So we have a node there at the surface, and then an antinode at the opening of the tube. So something like that. So it will look like this. Okay, and that's the tube. Okay. So what I'm trying to say is that L is equal to lambda over 4, okay? Because that's 1/2 of a 1/2 of a wavelength. Let me make a prettier lambda. Okay, so lambda over 4. I hope this makes sense. And how do we know that? Because, okay, the other lambda over 2 would be something like that, and then you need another lobe like that to create a full wavelength. So, but this doesn't exist, so this is an open tube, and these are the kind of waves created. Okay, so L is lambda over 4, which means that lambda is 4 times the length. Okay, so let's write that down again. Since lambda is equal to 4L, and because V is equal to lambda times F, we have that V is also equal to F times 4L, okay? Which means that if we solve for L, L is V over 4 times 1 over F, okay? So I'm gonna create a clean page. So since L is V over 4 times 1 over F, comma, the plot of L versus 1 over F, okay, will be a straight line through the origin with gradient equal to V over 4, okay? So V is 4 times the gradient, and the graph will look like this. You will have L and 1 over F, so something like this, okay? You cannot have a negative frequency, I'm sorry. So let me remove that part. So that's 0, so something like that. So you need to find the gradient. It's going to be delta L over delta of 1 over F. Okay, so I think that's enough. Let's move on to the next question. Nuclear physics, my favorite. So, question 7. Radon is a radioactive gas. One isotope of radon, Rn-220, decays to polonium PO by emitting an alpha particle. Complete the nuclear equation for the decay of radon. Okay, first of all, we have an alpha particle, and we know that an alpha particle is a helium-4 nucleus. So it has 2 protons, 2 neutrons, and it's written like that. So since the alpha has 2 protons, we need polonium to have 84 protons, and therefore it has 216 protons and neutrons, okay? Because that's 220 and that's 86, okay? I hope this makes sense. Polonium is used to poison people, by the way. I mean, I think I mentioned it in another video. So secret agencies use these kind of things. I shouldn't be saying this in videos, in YouTube videos. But anyway, so polonium is radioactive. All these isotopes are named by Marie Curie. She was from Poland. So yeah, that's named after her. I mean, she didn't name them. So, because, I mean, to honor her and stuff like that. And radon is a gas. And in the United States, where I used to live, they check the basements for the existence of radon because it's dangerous. Okay, so and that's actually that's the next question. So B, radon is produced in the ground and escapes into the atmosphere. Explain why this is a safety hazard. So radon is a gas that can be inhaled. Okay, so let me try to make better letters. Inhaled. Okay, once inside the body, okay, the alpha particles are highly ionizing, okay, and can damage. Let me use a clean page. And can, let me see, can damage living cells, okay, and DNA, etc., potentially causing cancer. Okay, and it is not in your curriculum, but it's good to know that I mentioned earlier basement. So why basement? So radon is really heavy. So radon has a mass number of 220. Okay, the other gases in the atmosphere are what? Oxygen 16. So with a mass number of 16, nitrogen 14. So really light gases. So because it's the heaviest, it sits literally in the bottom of things. So basements are in the bottom of houses. So that's why they check for radon gas. Okay, because it might exist there, and the reason is that some bricks, bricks that they make buildings with, they contain uranium, and in some decay chains of uranium, radon is produced. That's why they check the basements. So this can actually be an A-level question, in some form. I don't know. So anyway, let's move on to part C. The diagram shows apparatus for monitoring the decay of radon in the laboratory. Radon gas is produced in the plastic bottle from the decay of radium. A small amount of radon is then inserted into the decay chamber by squeezing the plastic bottle. A current is produced between two electrodes inside the chamber. So, I guess those are the electrodes. Let me use red. So, yeah. Okay. Where was I? A current is produced between the electrodes inside the chamber. This current is amplified and recorded by the ammeter, which we see over there. Okay. Okay, question I. Explain why a current is produced in the decay chamber. So the alpha particles emitted by radon ionize the air. Ionize the air inside the chamber. Okay. The ions and electrons produced are free to move. Okay. Under the electric field, okay, let's put an asterisk and let's move over here. So under the electric field from the battery, they drift towards the electrodes, okay, producing a current. And this needs a little bit of imagination. So you have the plastic chamber, okay, and that's the electrode, I guess, and you put the battery. So maybe you put the plus of the battery here and the negative there, and you connect, somehow you close the circuit by connecting it to the outside of the chamber. So there is an electric field established in here, okay? Now you have alpha particles entering this space. So initially nothing happens, but once the alpha particles enter, they collide with air. So oxygen 16, remember we mentioned that earlier, nitrogen and so on. So they create ions and electrons, okay, which because they are free to move, they move towards the electrodes, okay? So they create an electric current, okay? The movement of charge is electric current, okay? So it's this is the principle that governs how the Geiger-Müller tube works, pretty much. Okay, so there is another part of this question. So that there's a part 2. So let's do that too. A teacher is demonstrating the operation of the decay chamber to her class. She squeezes the bottle to introduce radon into the chamber. She claims that within 450 seconds, the activity of the radon in the chamber will be less than 1% of its initial value. Assess whether the claim is correct, and we get the half-life of radon as 55.6 seconds. So let's calculate lambda, the decay constant. So lambda is ln of 2 over t1 halves. So ln of 2 over 55.6 seconds to the minus 1. So 0.0125 seconds to the minus 1. That's lambda, okay? And then we know that n is n naught e to the minus lambda t, but we want to find the percentage remaining, so we divide by the initial number of nucleons n naught, and that's equal to e to the minus lambda t. If we plug in numbers, we have minus 0.0125 times 450 seconds over seconds, so that cancels. In physics, by the way, in general, whenever we have physical quantities inside functions like e, like sine, etc., usually we have physical quantities that are dimensionless. So lambda times t gives you a dimensionless number. Okay, so that's a general rule in physics. Anyway, so this is equal to 3.66 times 10 to the negative 3, negative 3, excuse me, which is 0.37%, which is less than 1%. So the teacher was right. So teacher is right. Okay, this was question 7. Let's move on to question number 8. Okay, question 8. A student investigated the behavior of a pendulum. The student used a spring gun to fire a small sphere of modeling clay at the wooden pendulum bob as shown in figure 1. The clay stuck to the pendulum bob, which swung to one side as shown in figure 2. Describe how the principle of energy conservation and the principle of momentum conservation apply to the situation. Consider the situation from the instant the spring gun is released to the instant the bob reaches its maximum height. This is another long writing problem, another long writing question of 6 marks. So paper 3 is I don't know, it's a physics from hell paper. So anyway, let's answer it. So when the spring is released, okay, elastic potential energy stored in the spring, okay, converts to kinetic energy of clay. Okay. The clay has momentum just before it hits the bob. Okay. When the clay hits the bob and sticks, momentum is conserved during the collision. Okay. The total momentum before equals the total momentum after. So, I mean, that's unnecessary to write. So, this is what I mean. Kinetic energy is transferred from the clay to the clay plus bob system. So, from the clay, so from here, what am I saying? From the clay to this system, which is the clay plus bob system, so the orange one. So kinetic energy is transferred from the clay to the clay plus bob system. Okay. Okay, the collision is inelastic because they collide and stick together. Okay, those collisions are never elastic. So the collision is inelastic. So kinetic energy is not conserved, and some energy converts to heat or sound. Okay, there's one more thing I want to write. So after the collision, okay, the kinetic energy of the clay plus Bob system, okay, is converted to gravitational potential energy as the when the pendulum, when the pendulum reaches its maximum height. Okay, these problems are not really hard, but you need to think about how to formulate them, how to write the sentences. So they end up feeling like hard questions. So anyway, let's move on. Part B. When the modeling clay hits the pendulum bob, the pendulum swings to one side. Show that the time taken for the pendulum bob to move from its lowest position to its highest position is about 0.6 seconds, and they give you the effective length of pendulum. Okay, I had to stare at this for a few moments because I was like, how on earth are we going to calculate this? And then I realized that they meant that you have to treat it as a pendulum, okay? So the pendulum has a period of 2 pi, this is an equal sign, I'm sorry, 2 pi times the length over g. So the length here is 1.25 and g is 9.81 on Earth. So the period is 2.24 seconds, okay? But remember that when we have a pendulum, it starts right there, and then it moves to the maximum height, then back, then all the way to the left, and then again to the center. So I'm trying to say that what they ask is 1/4 of a period. So t is t fourths, so 0.56 seconds, which is about 0.6 seconds as they state to go from the highest position to the lowest. Okay. Question 2. The pendulum bob was then attached to a spring of stiffness 0.12 newtons per meter. When the bob was displaced vertically and released, it oscillated with a time period equal to that of the pendulum. Calculate the mass of the pendulum bob. Okay, so now the period is going to be 2 pi times the square root of m over k. If we square this, we find 4 pi squared m over k. So m is what am I saying? K t squared over 4 pi squared. So 0.12 newtons per meter times t squared, which is 2.24 squared, so 5.02 seconds squared over 4 pi squared, and the answer is 0.015, and then the units, a newton is 1 kilogram times meters times seconds to the minus 2, and then we multiply by seconds squared, so that cancels, and we divide by meters, which cancel, so 0.015 kilograms. Okay, so this was question 8. Let's move on to question number 9. Okay, let us move to question 9 now. A student carried out an experiment with a light-dependent resistor, LDR. He connected the LDR in series with an ammeter and a power supply, as shown in the circuit diagram. Okay, the student placed the LDR a known distance from a desk lamp, as shown. Okay, the student noted the reading on the ammeter as he brought the LDR closer to the lamp. The student planned to vary the intensity of light incident upon the LDR by adjusting the distance x between the LDR and the lamp. So this distance, I guess. So let me use a red color. So this is the distance, okay, from the lamp. Okay. he thought that the intensity of light on the LDR would increase uniformly if he increased x by equal intervals. He therefore planned to take ammeter readings as he decreased x from 20 centimeters to 10 centimeters in equal intervals. Criticize the student's plan for data collection. So first and most important is that light intensity, so light intensity, follows an inverse square law. So follows an inverse square law. And specifically, the intensity is equal to the power of the lamp over 4 pi x squared. Okay? So intensity does not decrease uniformly as we, it's better to say does not change uniformly as we change x. Okay, so the other thing we can write is that equal steps in x will give unequal steps, unequal steps in intensity. Okay. So the data will be okay. So the data will be unevenly spread. Okay, and one more thing. Let me use a clean page. The student should decrease. The student should decrease distance at increasing intervals. Okay. And use a greater range of distances for better results. Okay, so I think this is a good answer for this problem. Let's move on to part 2 of the same problem, this question 9. Explain one precaution that the student should take to ensure that results are accurate. So you have to work in a dark room. So work in a dark room to avoid light pollution. Okay, so any light from the room would add to the ammeter reading, to the ammeter reading. Okay, now part B, explain why the ammeter reading increased as the LDR was brought closer to the lamp. Your answer should include reference to the charge carriers in the LDR. Okay, so as the LDR moves closer, to the lamp, okay, more photons hit the LDR surface. Okay, these photons promote electrons from the valence band to the conduction band. Okay, which means free carriers are released. So we can write releasing free charge carriers. Okay, let's use a clean page. the number of electrons, so the number of actually free electrons per unit volume increases, so the resistance of the LDR decreases. Okay, so using I equals to NQVA, current is proportional to N. Okay, so current increases as the number of charge carriers per unit volume increases. And this was question 9, guys. Okay, again, another long problem. I mean, a lot of writing is involved in this paper, so I'm kind of surprised. I feel like this is difficult for students. So let's move on to question number 10. Okay, question 10, jumperoo, I don't know. Let me know what this thing is in the comments. I've never seen this before. So a jumperoo is a harness suspended by a vertical spring into which a baby can be placed as shown. Okay, I don't know if I would put a baby on something like that. Probably not. Most certainly not. So, but anyway, let's move on. The jumperoo is adjusted so that the baby's feet are a few centimeters above the floor. So the baby is flying, something like that. Okay. If the baby is then displaced downwards and released, he oscillates vertically. The graph shows how the acceleration A of the baby depends upon the displacement x of the baby from its equilibrium position. Okay. So the typical A equals minus omega squared x graph with the negative gradient and so on. For safety reasons, it is suggested that the maximum velocity of the baby should not exceed 0.5 meters per second. Assess whether it is safe for the baby to oscillate in the jumperoo with an amplitude of 22 centimeters. Okay, so the maximum velocity in an oscillation is equal to omega times A. Okay, and as we just said, A is minus omega squared x, so the gradient of this graph is equal to minus omega squared, so delta A over delta x will give you the gradient. So I took the extreme values, so this value there and the origin to make it easy, so I use those 2 points. So delta A is 20 in the numerator, so 20 minus 0 pretty much, so 20 minus 0 over minus 5 minus 0, which yields, let me think, minus 4 centimeter per second squared. So let's come back to the other page. So this means that omega squared is 4 radians squared per second squared, which means that omega is 2 radians per second. So Vmax is 2 times 0.22, and that's in meters per second. Okay, so 0.44 meters per second, which is less than 0.5 meters per second, which means that that's safe for the baby. Okay, B. The amplitude of the oscillations quickly decreases, so the baby has to push down on the floor to maintain the oscillations. Would a baby do that? I don't know. So when the baby pushes at a particular frequency, the amplitude of oscillation increases to a maximum. What does that mean? Resonance. A baby of greater mass is placed in the jumperoo. This baby pushes on the floor at a frequency that produces a maximum amplitude of oscillation. Explain how this frequency compares with the frequency of pushing of the original baby. A calculation is not necessary. So for resonance, okay, for resonance, so max amplitude, the pushing frequency, the pushing F must match the natural frequency of the system. Okay, adding a greater mass, adding a baby of greater mass, okay, increases the period. And recall that the period is 2 pi the square root of m over k. So if m increases, the period increases. Okay, so as the period increases, though, frequency decreases. Okay, so the heavier baby, okay, pushes at a lower frequency than the original baby. Okay, so this was question 10. Now let's move on to question 11. Okay, question 11. A student connected a voltmeter to a potential divider as shown in the circuit diagram. The potential divider was adjusted by moving a sliding contact S from position position X to position Y. So from here to there. Explain how the voltmeter reading V depends upon the position of S. So when S is at position X, the resistance is 0, so the voltage is 0, right? So I'm talking about, let me erase that. I'm talking about that position, okay? So there is no resistance there, okay? Let's move on. As S moves towards Y, okay, the resistance between X and S increases, okay, increases proportionally to the length XS, okay? So potential difference is divided in proportion to the resistance. Yes, in proportion to the resistance, excuse me. I got confused. Okay, V increases steadily as S moves from X to Y, okay, reaching the full supply potential difference when S reaches Y. Okay, let's move on to part B. A filament lamp and ammeter were connected to the potential divider. The potential divider was used to vary V across the filament bulb. The ammeter gave the corresponding current I in the filament. I varied with V as shown in the graph below. Explain the shape of the graph. So as V increases, I also increases, okay? And the filament is heated, okay? So T increases, right? So the resistance of the filament increases with temperature, okay? So each unit increase in V produces a smaller increase in I, okay, the current. So the curve, the graph curves, excuse me. So the graph curves showing a decreasing and decreasing gradient. And the gradient in this case, so that's the gradient which decreases. Remember that R is V over I, which means that I is 1 over R times V. So the gradient is 1 over R, okay? So the gradient goes to 0 as the resistance goes to infinity. That's why it gets flat. I mean, eventually the resistance gets really high, okay? Because the filament heats up. Okay, let's move on. Part C. The temperature T of the filament varies with the potential difference V across the filament according to the expression T equals to A times V to the B, where A and B are constants. Explain why a graph of log T against log V would give a straight line. Let's take the log of both sides. So log of T is log of A plus log of V to the B, which we can write as log of T is B log V plus log A. This has the form Y equals to mx plus C. So the gradient is going to be B, and the y-intercept is going to be log A. Okay, so you can use this graph to find B and A, and also it's going to be a straight line. Okay, let's write it here. Actually, we didn't write it, so straight line. Okay, data for T and V is shown in the table below. Plot a graph of log of T against log of V on the grid opposite. Use the extra columns provided to show any processed data. Okay, so let's create the column of log of T and log of V. So for the first value, you have 3.17 and 0.7. And yeah, I'm gonna fill the table now. Okay, we have the values. We are ready to plot the graph now. Okay, let's draw the axis. Okay, this looks okay. So this is going to be, let me think, log of T. Oops. This is what they ask, right? Log of T, okay. And let's make this log of V. And we see that the log of T increases from about 3.15 to about 3.40. So we are going to take increments of 0.05 starting from 3. Let's make this, okay, let's make this 3.15, 3.20, 3.25, 3.30, 3.35, and then 3.40. I think this is going to work well. And then for log of V, we increase, we go from 0.7 to about 1.2. So I'm going to take increments of 0.1 starting from 0.7 over here. Okay, 0.7, 0.8, 0.9, 1, and then, oops, this is 1. This is, I confused myself. What did I do? 1, 0.7, 0.8, 0.9, 1. Yes, 1.1. And this is finally 1.2. This is all the range, so that's good. So note that our graph does not start from 0. This is actually 0.6 for log of V and 3.10 for log of T. Okay, so we cannot really find the y-intercept directly, okay? But I don't think they ask for it. But anyway, let's make the plot. I'm going to show you the first pair of values, and then I'm going to speed up the video. So the first pair is 0.7 for log of V and 3.17 for log of T. So let me think. So 0.7 and 3.17. Every little increment over there is actually 0.005. So that's the point, right? I think so. Okay, yeah, that's the point. So, yeah, I'm gonna draw the other ones. So, okay, these are all the data points. Let's draw a line of best fit. It has to pass through all the points. Okay, something like this looks good to me. Okay, so we have a line of best fit and we have our plot. Let's move on. Determine a value for b using your graph. Okay, so as we said, the gradient is equal to b, which is equal to delta of log t over delta of log v. And I take the extreme values. It's a usual technique I use. So I take these pairs. It is safe usually to find a good estimation. So 3.36 minus 3.17 for the numerator, and then 1.18 minus 0.7. So this yields 0.4 for B. Okay, so this is our answer. And notice that these 2 points are actually on the graph, so we can use them. But you can use any 2 points on this line, even here. Like if you take a point there and there, it's still fine. And a point there and a point there, it's still fine. So any pair of points that you love. So let's move on to the next and I think last question. So let's do that. Okay, question 12. Chocolate is a solid at room temperature but melts just below body temperature. A student investigated the viscosity of some melted chocolate using a falling ball method. Since chocolate is opaque, a thin rod was attached to the ball so that the movement of the ball could be monitored. The apparatus is shown in the diagram. So you have a measuring cylinder, a rod, a ball, and melted chocolate. The chocolate was maintained at a constant temperature during the investigation. Question I, the student used a stopwatch to measure the time t for the ball to fall 22.5 centimeters whilst traveling at its terminal velocity. Here results are shown in the table. V is given by the formula, and the formula is kind of strange because it misses some important things there. So I figured that that's rho B and then rho C. Actually, let me rewrite it. So I don't know why it was printed funny, but this is actually 2r squared G and then rho B minus rho C over 9 times the viscosity, okay? Where R is the radius of the ball, RB is the density of the ball, RC is the density of the chocolate, and eta is the viscosity of the chocolate. By the way, let me show you what physics is all about. So if you take this expression without knowing what the other quantities should be, you can immediately infer the units of the dimensional units of those expressions. So on the left-hand side, we have a velocity, so the units are meters per second. On the right-hand side, we have r squared, so meters squared. And then G is given in meters per seconds squared. Okay, so we have something that is given in meters to the cube times over seconds squared. Therefore, this thing has to be multiplied by probably some density, because density is kilograms over cubic meters. So this cancels the cubic meters. And then we need something in the denominator to get rid of the kilograms and make meters appear into this picture. So that will be probably something with units of Pascal seconds. Okay, so let's try that. So viscosity has units of pascals times seconds. Okay, so if we put that in, we have units of kilograms over second squared, and then we have, what did I do? This is Pascal seconds. Okay, that's an equal sign. Sorry, I got confused. And then we have pascals is newtons over meter squared. Okay, and we can multiply that extra second with the second squared to get seconds cubed. I hope I didn't lose you. So we have kilograms, meters squared over seconds cubed, and then newtons is kilograms times meters per second squared. Okay, so everything cancels and we are left with meters per second. So you can kind of reconstruct the formula even without knowing the formula, I'm trying to say. Okay, anyway, but for some reason it didn't print properly, so that's the formula we will be using. I hope I didn't lose you. Stay with me. So let's move on. The graph is taken from a commercial website. It shows how at the temperature of the experiment, eta depends on the percentage of cocoa in the chocolate. The chocolate wrapper indicated that the chocolate had a 35% cocoa content. Assess whether the student's timing data supports the percentage cocoa content. Okay, this is this is like a long problem. So first of all, let's go here and find the average time. Average time is of course t1 plus t2 plus t3 over 3, or 9.7 seconds. Okay, now the velocity is simply distance over time. How do we know this? The expression is 0 since v is v terminal. Okay, now so v is then 0.225, which is 22.5 centimeters that the ball covered in the chocolate, over 9.7, which yields 0.0232 meters per second. Okay, now if we go to the graph, from graph, so basically we need to compare this measured velocity with the velocity we get if we apply this formula. Okay, so from the graph we need the viscosity. From the graph, if the cocoa content is 35%, okay, eta, the viscosity, is 4.9 pascals seconds. So it's this point over there. Okay, so you can read it off the axis. So 4.9 pascals times seconds. Okay, now let's use the formula in a clean page. So v is 2 times, and then the radius squared, 4.25 times 10 to the negative 3 squared, okay, times g, times the density of the ball, minus the density of the chocolate, over 9 times that viscosity, 9 times 4.9, and this actually gives us 0.0515 meters per second, which is larger than what we just calculated, 0.0232 meters per second. So the student's timing does not support the formula, the cocoa content. Excuse me, this is what they ask, right? Yeah, the cocoa content. Okay, so let's move on. Part 2, explain one reason why the student's data may have led to an inaccurate conclusion about the cocoa content. So T of chocolate may not have been constant. That's one reason. And then eta depends strongly on T. So any variation affects the experiment. Okay, moving on. Part B. Uh, One type of chocolate melts at a temperature of 32 degrees Celsius. The energy released when 65 grams of this chocolate is digested is 345 kilocalories. This is how it's called, right? It is suggested that the energy used to melt the piece of this chocolate is at least 15% of the energy released when the chocolate is digested. Assess the accuracy of this suggestion. Okay, first of all, let's find the energy to melt the chocolate. This is going to be equal to the specific heat capacity of the chocolate times the mass of the chocolate times delta theta to raise the temperature to 32 degrees plus the mass of the chocolate times the latent heat um, for um, for the chocolate. Okay, let's plug in numbers. 3.9 times 10 to the third times 0.065 kilograms times 17 degrees because we go from what was the initial temperature? From 15 to 32 degrees plus 0.065 times 1.5 times 10 to the 5. And this yields 14,060 joules. Okay. Now 345 kilocalories is actually, let's convert to joule. They give us that 1 kilocalories for 1,200 joules. So 345 times 4,200 yields 1,449,000 joules. Now 50% of that is, let's calculate it, 50% of that is 217,350 joules, which is larger than 14,060 joules. So claim is false. Okay, so this was paper 3 from 2024. I have to say, I think it was a difficult paper, not because there was anything fancy in terms of physics, but there were many questions that needed to be answered and many things to write down, etc. Anyway, I hope these videos are useful. So far, I never received any help from anyone using my PayPal account that I list there. So I used to have a buy me a coffee link. So I'm gonna try to use that in case you want to help the effort I'm making with these videos. So I'm gonna list the buy me a coffee link at some point. Thanks for those of you who provide really nice comments in the videos and feedback, and they support what I do. Still, 90% of the people who watch these videos are not subscribed, so it would be nice if you guys subscribe. So summer is coming, so at some point these videos will slow down because I will probably focus on some research I want to do, physics research this time. I don't know how it's gonna happen, but we will see. Yeah, this is it. See you in the next video, guys. Hope these videos are useful again, and good luck with your exams. Bye.